happy to see you all here tonight. I'm Natalie, your representative from AstroTours, which is a grad student-run set of tours that happen every month. But you're all here for our special event this month to celebrate EarthHour. Glad you came, even in spite of the dip in the temperatures, and I'm happy to say we have clear skies for telescope viewing after the talk tonight. You'll find information about what's happening after the talk in your brochure, where you'll also find a feedback form. Since we are grad students doing this with volunteering time, we really want to hear what you have to say about our work, so please be honest and answer completely. We'll leave bins for you to leave your feedback forms after the talk. Without any further ado, I'd like to introduce tonight's speaker, Professor John Morris from York University, and he's going to help us answer the question, what if the Earth were no longer habitable? So let's give him a hand and welcome here.
Well, first of all, thank you all for coming out on such a cold evening. Always fun to be up with the telescopes when it's nice and cold. As you just heard, I am a professor at York University, but that's sort of my day job. I also work a little bit with rovers and other spacecraft for the solar system, and really my training is in planetary science. So what I tend to do day to day in my science is I try to understand a lot of what's going on with the atmosphere, with the surface of other planets, and how they got to look the way that they did. And when I'm doing these kinds of problems and working on them, it almost seems to come back time and time again. There's one common thread that comes together, and that's the question of planetary habitability. So what I want to do today is sort of walk you a little bit through what it is that we mean by planetary habitability. What is it that makes a place habitable? Why is it that the Earth is such a great place for life? And how do we know about the potential for habitability other places in the solar system? I'm showing up here a lovely piece of artwork prepared by the Propulsion Lab. This is what an artist thinks it might look like if you were standing on the surface of an exoplanet by the name of Kepler-16b. We don't know a lot about Kepler-16b. It's really just a dip in a light curve, insofar as we can tell. We can figure out how far away it is from its sun. We don't know if it's a gas giant or a rocky planet. The artist feels more on the rocky side, as you can see here. But one thing that we do know about this place, it's probably not very habitable as things go. And that's why our little astronaut here is wearing a spacesuit. The temperature of this place is somewhat colder than dry ice, more than 90 degrees below 0 centigrade. Not a great place to be caught out in the cold, not quite. And here, we're not quite that cold tonight, even though it's feel like it a little bit. But it's got the two suns, which are interesting as well. So what I want to do first is sort of walk through what it is that makes a place habitable in the first place. And to do that, I want to start a little closer to home. Not all the way. This is where I normally hang out on a daily basis. This is an image of Mars taken by the Spirit rover, which is unfortunately no longer with us. On the surface of Mars, it's not a very habitable place today, but we can probably figure out a nice, easy way to make this look a little bit more like home, to make it look like a more hospitable place to spend some time. So, for instance, if we are talking about NASA, often we hear the term falls of water. And in fact, if we just add water to this, I guarantee you it'll look a lot more fun. I wouldn't want to spend a vacation here, but this might not be bad. All that has happened here is taking that image from before. Keep your eye on this sort of cleft stone here. And you'll see adding a liquid water. Already just adding water makes it seem that much more habitable. And in fact, one of the most important, perhaps the most important characteristics for planetary habitability is the ability to have that liquid water on the surface, or maybe even under the surface as well. We go out to the Galilean moons, and in the outer solar system, you have places that have their own internal energy source. They're solid on the outside, but maybe they're liquid on the inside, and who knows what's going on in there. This would be a fascinating place to go and explore, let me tell you. And I'd be keen to see this happen sometime in my lifetime. But it's a tough technological problem. Now, that's the first aspect of planetary habitability, having that water. We can talk about the second. Might it be an atmosphere? Well, it turns turns out that if you have water on the surface, an atmosphere really helps you. Having all of that gas there keeps that liquid water from boiling away. If you have ever heard of people who climb mountains, as you get higher and higher in the Earth's atmosphere, the boiling point goes down and down and down. If you disappear the atmosphere completely, then things just evaporate into space and the water that's left will freeze solid. Not a very habitable place. So if you're on the surface, you need that atmosphere. But if you're under the surface, then you can make do without. So I'm not going to put atmosphere onto our list of necessary attributes for planetary habitability. Let's talk about temperature. That's another good one. We need a place that's not too hot and not too cold. Right here I'm showing Io, the most volcanically active body in the solar system. It's the closest moon into Jupiter, and we regularly see enormous volcanic eruptions, calderas full of lavas on its surface. Not a great place to go hunting for life. Similarly, here's Mars. You can see a little snowfall up here that's taken place at the Viking 2 lander site. And down here we've got a lovely picture from orbit, really a symphony in frozen water. So Mars has the water, but just not in the right form. So not too hot, not too cold. It's good for maintaining water. That's not all it's good for. In fact, it's very critical, it's very important to have just the right temperature if you want to form the kinds of molecules that make up life. The reason for that is that life depends on carbon. It's just such a versatile molecule. Some of you may have heard of potential life based on other atoms like silicon, but silicon cannot do nearly half the things that carbon can do. So as you increase the temperature of the surface, those little molecules tend to link up with each other faster and faster, forming the long carbon chains that make up all of the intricate pieces of us, things like DNA and whatnot, that are critical for life. But if you continue to crank up the thermostat on your planet, even hotter and hotter, then those individual molecules start to move so fast that the polymer chains break down. It's just like putting a piece of plastic in the oven. It doesn't end well. So that's another thing. We need to have it not too hot, not too cold. We need to have the liquid water. We also need to have a couple of different kinds of protection. We need to have some protection from radiation. Not only because radiation like ultraviolet radiation and even stronger stuff like X-rays and so on, not only because this stuff can take those lovely carbon chains apart, but if you have enough of it and you don't have enough protection, you can actually strip away the atmosphere, and that starts to challenge whether or not you can have a liquid water on the planet. This is a little visualization from the Maven spacecraft, which is in orbit around Mars, just taking its results and putting it into a form that we can see. And even in the present day, there's a lot of atmosphere being stripped away from Mars because there is protection from us. It's our magnetic field, by the way, that keeps us a little bit in better shape than Mars. That's not the only thing we have to be afraid of. We also need to have some kind of protection from major planetary disasters, cataclysms, things like asteroids coming in and striking the Earth. Early on in the Earth's history, this happened with a lot of frequency. You even had areas on the surface which might have been melted for long periods of time, creating magma oceans, perhaps something like up here. This period of early high bombardment is actually referred to in the geologic literature as the Habitable period, quite fittingly. So what happens in a solar system like ours is we have a large planet like Jupiter, which can help to clear out a lot of the debris after planet formation. And that gives some space for the planets themselves to develop without having to reset the clock every time you get smacked by something like this. There's another factor, fifth factor, nutrients. Just about all the life that we know on the Earth is made up primarily of 6 different elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All of those coming together. And it turns out that even on the Earth, we have sort of limits on life. If you were to increase the limiting element, you could really have huge booms. And typically on the Earth, it's nitrogen and phosphorus that are the ones that are limited. which is why when you go out to the store and buy fertilizer, you find a lot of nitrogen and phosphorus like those. Now, we tend to use that fertilizer on our lawn and in our agriculture and in our cities. And if you look up here, this is Detroit. And you'll notice that the runoff from Detroit, as it heads down here to Lake Erie, you can see it in color. That's not because there's so much fertilizer that it's changing the color of the water. What's happening is that in those areas, we actually have enough nutrients to get the algal blooms going. They take it up and they just go completely nuts. And so you get these lovely, if possibly disturbing images from water that we see, like this. Now, you might wonder why nitrogen is one of the limiting elements. Certainly, the atmosphere is made up 79% of nitrogen. Why is it that plants and other life on the Earth can't just use the nitrogen? Well, it turns out it's in a form that's not available to be used by life. And in fact, you can imagine the Martian surface. This is another place where we actually do have carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All that's there, but it's not in a form that's accessible. So if any of you have seen The Martian, you'll recall that he wasn't able to grow his potatoes in the Martian soil right away. He had to add a certain something extra brought along from the Earth. For those of you who haven't seen the movie, he sort of invaded the toilet here to get him the nutrients that he needed to make his plants grow as nicely as they did here. So you need to have these elements, you need to have them accessible. And a lot of the history of life on the Earth is making more and more of the inorganic forms, as we call them, of these elements into forms that can be used by other types of life. So those are 5 things. Everybody's got their own list, and some of them are quite long. The problem we have is that on Earth, we have only one example, really, of life. All life on Earth is related to every other piece of life. And because of that, we don't know exactly what's special about the Earth. We can get a long way there. And there's one question in particular that really challenges us, and we're not there yet. So I'm going to add a 6th element to planetary habitability. It's a certain something mysterious. How do you start off life on the surface? How do you go from a place that is habitable to a place that is inhabited? We don't know yet. We're still working on that. But there's a famous experiment that gives us some hints. This fellow up here is Stanley Miller. And he had a famous experiment that he did when he was a graduate student with Harold Urey way back in 1952. What they did is they took the simple compounds that are available in the early solar system and would have been present in the early Earth's atmosphere. They put them into this lovely flask here. There's a little bit of liquid water over here. Don't need that. And they started to hit it with an electric charge, essentially recreating lightning. You do this for long enough, and it doesn't take that long, you start to create all those complex organic molecules into the beaker. Now, nothing, of course, sort of climbed out of that beaker at the end, but at the same time, there's a way here to create, on the surface of planets, with liquid water and with these simple compounds, a whole soup of material that you could use to try to start up. We don't know exactly the pathway from here, but this is suggested. Now that we have some idea of what it is that we need for a place to be habitable, let's take our knowledge out into the solar system and look for other habitable environments. So this is a good place to start. This is a lovely report by NASA on astrobiology, which is the study of life away from the Earth, which is a fantastic name, and especially because we don't actually have any examples of any life exterior to the Earth. So really, astrobiology for now is the study of habitability. And at the bottom of this lovely piece of cover art here, we've got the Earth. Nice and familiar, we know there's life there. And then as we go up, we see other places where we wonder. Places like Mars, places like the icy moons. And the comet here is included not just because it's pretty, but because we find some of these complex organic molecules in comets as well. So there's some interest here. Let's start with the Earth. always good to start with what you know. The Earth we already know is habitable because we're here. So let's review. For the Earth, we've got 70% of surface coverage with liquid water. So our first criteria, that liquid water, is nice and satisfying. And we know that there's a hydrological cycle. We know that that water is evaporated, it falls as rain, it's available all over the planet. We can see that because of all of these white areas, all the clouds. The reason that that liquid water is able to persist is because we've got this really nice dense atmosphere. And at the surface, the temperature is just right to keep that water liquid, about 288 Kelvin or 15 degrees above zero. That might actually surprise somebody who's looking at the Earth from another system, wondering where the Earth is in our solar system. If you were to take the equilibrium temperature, which is the temperature that a piece of material at the orbit of the Earth would come to roasting in the sun, it's not 288 Kelvin. It's actually 254, minus 19 Celsius. Why is there a difference there, 34 Celsius? Anyone?
The atmosphere conducts heat, greenhouse gases and such?
That's right, the greenhouse effect. Greenhouse effect is actually a good thing. You can't have too much of a good thing, it's true. But without it, the Earth would be frozen solid. Now we also have that protection from the ultraviolet with our ozone layer. And we also have lots of nutrients on the Earth, really quite abundant. Now, as we look over the planet, we can see some places where there's more life than others. There are places that are green, and there are places that are sort of more desolate looking. But the interesting thing is, as we go around the planet, most places that you would think would just be completely desolate and uninhabited actually have things in them. So even these extreme environments have life. This here is an image of a hot spring at the Yellowstone National Park in the United States. And all of the colors that you see here, all these vibrant things, are all due to different forms of microorganisms, different forms of life. We can go to places like this that are very warm. We can go to places like the Atacama Desert that are very high up. They don't see much rain at all. It's very cold, and there's a big swing of temperature night and day. But yet we find lots of things up here, including these flamingos. We can go to even stranger places. We can go to the bottom of the ocean with incredible pressure. We can go near volcanic vents called black smokers near the bottom of the ocean. When we do that with submarines that are one step away from spacecraft, we find aliens, or at least life that looks alien to us. These sort of chimneys of black smokers in water that can be as hot as 400 degrees Celsius are just teeming with life. And this is a whole ecosystem that has nothing to do with the sun. It's completely separate. The light down here we call chemosynthetic because it deals with the chemicals of what's coming out of this vent. It has nothing to do with what's happening with the sun. So this is really interesting. We'll come back to this a bit later. Now, there are a few places on Earth that do seem to be devoid of life. If you go, for instance, to some of the dry valleys in Antarctica, not only does it look desolate, but it can actually be pretty lifeless too. There was a search done by McGill a couple of weeks ago that was in the news here. They went to one of the valleys in the Antarctic dry valleys and could find no evidence of any kind of working, metabolizing life at all in this place. But looks can be deceiving. Even though this place looks desolate, other places that look equally desolate might not be lifeless. For instance, if we dial the clock backwards to the early Earth, there's an awful lot of places that look like this, and they're not all lifeless. For instance, here's sort of a modern-day throwback. This is Shark Bay in Australia, and we've got all of these rock-like things up here. These are all microbial communities. They're stromatolites, we call them. And what you're seeing here is actually an explosion of life and habitability. So we need to be able to understand really what it is that habitability means without having to actually see the inhabited part of it. And so let's go to Mars, a place that's not obviously a great candidate. Mars is a bit of a different place from the Earth. If you look at it, there's no liquid water at the surface, none at all. We do see solid water if we look at the northern polar cap, You can also see water ice clouds down here, near the volcanoes especially, but no liquid water at all. The atmosphere is very, very thin, 1/100th of the thickness of the Earth's atmosphere, and it doesn't give Mars any greenhouse advantage at all. The average surface temperature here is 210 Kelvin. That is about 60 degrees below zero, on average. And it changes by about 100 degrees from day to night. There's no insulation at all, basically. The surface is contaminated with a very powerful oxidant called perchlorate. This was first suspected from the Viking missions and actually seen and identified by the Phoenix mission in 2008. And perchlorate, if you're curious about how it interacts with life on the Earth, we often use this to clean toilets. So it's not really something that's very kind to most kinds of life in general. But the interesting thing is that Mars has all of those nutrients as well. It makes you wonder, what about ancient Mars? What if you turn back the clock here as well? And in fact, many people think that if you go back to early Mars, it might have been warmer, it might have been wetter, it might have even looked perhaps something like this up here. Something more akin to the Earth, with oceans. We even see areas that look like maybe they used to be oceans on Mars. We also wonder, because of the way that Mars's orbit changes over time, whether or not it periodically comes back to life just a little bit. Now, let's zoom in and see why people might think that there might have once been liquid water here. If we look at a couple of the formations that we see on the surface, frozen and written into the rocks, you get a feeling that this was a place where something was going on in the distant past. Here is a lovely formation from a place called Ebberswalde Crater. Here, what we've got is a fossilized delta. You can see where a river ran out into a flat area and deposited all of a sudden. It built it up, and that's what's left here. It looks very much like the Mississippi River Delta here on the Earth, which gives us our hint. And in fact, the Spirit rover was sent to a nice flat place called Gusev Crater out here. The reason it was sent to Gusev was because Gusev is linked up to this 800-kilometer long valley called Madam Vallis that looks like it was once a river channel. So there's definitely a lot of evidence on Mars that at one point in time we did have flowing water. And each new mission that we send describes and discovers more and more about this. My most recent mission that I've been part of was Curiosity. Here's a lovely view of Mount Sharp. And what do we see? Layer on layer upon layer. These are materials that were set down in liquid water in a marine environment. And if you think that the Grand Canyon is spectacular with all its layering, this is 5.5 kilometers tall. It is actually the thickest sedimentary layered stack in the entire solar system. Fantastic place to explore. It's not just the large scale, it's also the small scale as well. We can proceed in and we see all these ancient shorelines all in a row. And when we look at the individual rocks, here's one that's just a half meter across. It may be a little hard to see, especially in the back, but this one is a whole bunch of little layers as well, coming back and forth, preserved here. It makes you wonder, having had liquid water in the past, it probably was the right temperature. We know that the nutrients are here because we drilled into these rocks and we found them. It makes you wonder whether this was a habitable place and whether it was inhabited. As Mars moved more towards the present time, however, things dried out, things became more arid. And so now we don't see anything at the surface. But we have to wonder whether maybe life went underground. This one makes us really suspicious. A few years ago, there was a team in the United States that had a look at the Martian atmosphere. And they were looking for a very special molecule called methane. Now, on the Earth, we think of that as natural gas. We may associate it with cattle. But on Mars, it's really strange to find a thing like methane, especially to find plumes of it coming from a part of the planet called Noe Thase, where the surface is all sort of cut out. Now, there's two things that can give you methane like this. It shouldn't stick around on the planet, and the pattern that you see up here suggests it's being produced. You can make it if you have fresh rock being sort of dissolved by water that's warm at depth. The other possibility is microorganisms make this planet. So either way you cut it, this is an exciting story for Mars, and as we continue on with our exploration, this is something that we're going to be looking more at. Now, Mars isn't the only place in the solar system where we have the hint of habitability. If we go out to the outer solar system, and we consider the icy moons, I'm going to take you to Enceladus, which is the moon of Saturn, we also see a lot of potential for places that might be habitable. So for instance, here's what Enceladus looks like. At first glance, maybe this is not the most likely place to find it. We look at the average surface temperature, it's minus 198 Celsius. That doesn't sound like it's very good. We also have no atmosphere at all, not even a thin one, nothing here at Enceladus. We have no nutrients on the surface. We have direct exposure to radiation. It's a nasty place if you want to go for a walk here. But there is something interesting going on. If you look down here at these parallel stripes, we call them Tiger stripes, and you look at them at just the right angle of the sun, you see these things. These are geysers. This is liquid water being essentially pumped out of the inside of the planet. And what we think is going on here is that we've got this lovely global ocean sitting underneath this protective outer icy core, or sort of icy shell here. Down here at the south polar area, we've got the jets, which come out. On the inside, you have a rocky core. If the rocky core is actually in contact with the global ocean, well, then you've got a bonanza, because usually the nutrients that you find are in the rock. If they're touching the water can dissolve those nutrients, and they're then available for whatever's in the ocean. There's actually more livable volume amongst all of the different icy moons out there that are thought to be liquid on the inside. And who knows what's in there? It could be anything. It could even be something like this. Now that would be exciting. That would be, I think you could definitely get a Science or a Nature paper or cover the New York Times with a picture like that from spacecraft. But it's not just about exploration like that. We can also learn things about the Earth as well. And that's because, remember that that something special. We know on Earth that there are two theories. Maybe that life began on the surface, or maybe life began with those black smokers. Those two different ecosystems are cut off from each other, so either one might have been a start. What we can say with the moons and the other icy bodies is that there's really only one way to go. So if we are able to break into these giant oceans and we find them lifeless, that has implications for how things might have started on the Earth. Now, you put it all together, and you end up with something like this. The idea of a habitable zone, that within any solar system, there is a place where you can have habitability on the surface, and places where habitability is less likely. Just to explain this up here, we've got the Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto is still included on my plot. This is the distance from the star. That's the important thing, because the distance, how far you are away from that stellar fire, says something about hot or cold, and that says something about liquid water or not. If you turn up the heat on the star, then the habitable zone moves out, which is why it turns in this direction. If you dial back the heat on the star, down here, then the habitable zone moves in. We have drawn this in sort of a rudimentary way because we don't really know much better. We can look at Mars and we can look at Venus, and we can say, well, Venus is too hot and Mars is too cold. So the habitable zone has to be somewhere in between those two, which is really all you're seeing there. Now, the other factor that's not shown on this plot is that stars, as they age, get warmer and warmer. So this habitable zone here starts in closer to the sun and works its way out. And in fact, you can have places that begin habitable and become not habitable at all. You take a place like Venus, which is in many ways Earth's sister planet, very similar in size, very similar in composition. No reason to think that Venus didn't at one point have a large ocean just like the Earth did. Have all of those attributes that Earth now has. But these days, Venus' surface is hot enough to melt lead. There's essentially no water left. This is a hellish place. And what happened here is that if you push a planetary system far enough, you will break it. And so as a result of that, Venus had its oceans boil off, short-circuited all of the different ways that you can regulate the planet and keep it habitable, and this is what we're left with. So let's take a second and look at how it is that habitable zones actually stay habitable. This is an image of the Earth, believe it or not. At least the Earth, how it has looked several times in the history of the planet. Remember that at the orbit of the Earth, the equilibrium temperature, the temperature that you have if you just had a hunk of rock, is below zero. If you go further back in time, the sun wasn't as strong as it is now, so it was even colder. And as a result of that, runaway glaciation was a problem for the Earth throughout geologic history. We needed to have a mechanism to sort of stabilize the planet, even when the planet is pushed severely. By the way, this is referred to as snowball Earth, which has happened several times in the Earth's past. How do you fix snowball Earth? Well, there's a way to do it. There's something called the carbon cycle which can help you out here. And it sort of relies on the fact that even if you cover the entire surface of the planet with ice, you've still got volcanoes belching out things like carbon dioxide, things that are greenhouse gases into the atmosphere. And you do that for long enough, and you can push the place back up again. Here's how it works in a simplified form, which doesn't do anything right at all. So these are volcanoes. They emit carbon dioxide, which goes into the atmosphere. And it will go ahead and heat things up. However, there is a counterpoint to this, something that helps to regulate. You always need two things together, this give and take, to maintain the temperature. So the maintenance for this is the oceans of the Earth. The carbon dioxide in the atmosphere dissolves in the ocean. That forms carbonates. You can do that inorganically. You can also do it with things like coral reefs. And what we do have here is an extraction, removal of carbon dioxide from the atmosphere. Now, you let geologic time go on long enough, this carbonate sitting at the bottom of the ocean gets subducted by plate tectonics. And it evaporates, effectively, and becomes lava once again. So what happens here with this nice cycle going on, if you freeze the ocean solid, you get rid of the mechanism that takes the carbon dioxide out of the atmosphere. And it starts to build up and build up until you melt the oceans once again. So this is a lovely planetary regulation mechanism. Once you include life in the mix as well, then things get more complex. What's really interesting is that life probably had to restart on the Earth several times. You think of that Hadean period when you had lots of impacts coming in. You perhaps had a number of times when life started and then was destroyed. But once it gets a toehold, life, even bacterial life, tends to affect its environment and really tends to keep going. As it gets more and more complex, the range of life expands. At one point, the surface of the land was like the surface of the moon as far as life is concerned. But then we figured out it's harder to dislodge. And what I'm showing up here is the rise of oxygen over the period followed by the history of the Earth. So here is sort of a change, how life has affected even the atmosphere of our planet. We can think of this in terms of how we as humans use technology to expand our range to places where we would normally be comfortable. We certainly, without clothing, without technology, we would have a hard time outside today. And so even though we're creatures that evolve in a more equatorial area, we've been able to travel to every part of the planet. We have found ways to adapt ourselves, our technology here as proud Canadians, to be able to live in this kind of a climate for which we're not actually adapted as organisms. Another example that I'm a big fan of is the Polynesians down here, who developed a culture and a technology with these outrigger canoes for being able to hop between different little islands. It's like traveling to another planet, but still on the Earth. Our technology today can do even better. We can go beyond our own Earth to places like this, which are even more extreme. Here's Harrison Schmitt examining this house-sized boulder on the moon in 1972. And so, as you get more and more complex, as you get intelligent life showing up, then the range of places that are effectively habitable gets bigger and bigger. So I would like to propose here an intelligent habitable zone, a place with just a little bit of ingenuity, you can go and find a way to make do. So just like our previous habitable zone, I've increased it now to all the places where you can perhaps make a go of it. Now, science fiction is full of lovely stories of all of the places technology can take us. I'm not going to review all of them here. Mars has the most similar environment, at least at the surface of the Earth. So Mars probably is the sort of place that will be first. You can imagine things like this, where we grow our own food, a little bit like the Martian, but actually plant. And the little Canadian flag here on the habitat. So this is probably sort of the first place you're going. But there are other places that are more exotic yet. If you go to Venus, the surface is a bad place to be. But up in the clouds, you have the right temperature, you have the right pressure, everything looks nice. Why not something like this place? We've actually flown balloons in the Venusian atmosphere. Why not something more permanent? Makes you wonder. And if we go out to the Galilean moons, we've got all that ice. Ice is a great building material. All you have to do is melt it and move it out of the way or cut into it. And in fact, in Scandinavia, they enjoy doing this from time to time. There are ice hotels made above the ground, and there are also ice hotels that are cut into some of the glaciers there. And you can imagine the same sort of thing in a place like Europa, where you want to understand what's going on with access to the ocean, yet at the same time protect yourself from the radiation that we get by burrowing into that ice shell. Eventually, though, you'll want to go on past the solar system. You want to go out and sort of explore new worlds which may have something closer to the Earth, a place where making a go of it is a little bit easier. There's this idea of a galactic habitable zone, a place where you have just the right materials that you need to build planets that are more like the Earth. And in fact, when we go looking with missions like Kepler, we find a whole diversity of planets. We find planets made of things that we wouldn't have even thought of even 10 or 20 years ago before we saw it. So this just shows you some of the diversity. What I'm showing on here are all of the candidates, all of the potential planets discovered by the Kepler spacecraft. Here's the Earth here. We've got size going up and down here. So we've got our Jupiters up here, our Earths along here. This is the orbital period, how long the year is. So our own Earth would be at about this spot. And what you'll notice is that there's a planet up here for just about any orbit, any distance from its star, any size that you can think of. It's out there somewhere, just waiting to be found. But for now, this is the only place that we know of that has just the right conditions, those 6 magic ingredients, to be perfectly habitable, all on its own, and have all of those things in abundance. So let me, on this Earth Hour, leave you with just one more slide here. The key thing is water. And this is a lovely piece of artwork from a book called Alien Seas. And this image is called Water, Water Everywhere. It imagines an astronaut who's going out to a place very similar to the Earth, but maybe not exactly the same. He's a little afraid to take off that spacesuit, even though things look very, very inviting. And let me just share one final quote from Carl Sagan. As a planetary scientist, I can't have a presentation without a Carl Sagan quote. The surface of the Earth is the shore of the cosmic ocean. Lately, we've waited a little way out, and the water seems inviting. Thank you very much. with some microphones being set up. And I think we have to get out of here fairly quickly, so I think there'll be a bit of time for questions after the fact as well.
Yes, if you're able to go up to the microphone, you're welcome to line up over there. Otherwise, I can choose someone from the audience now. You had your hand up. You in the red hat. Yes.
Yeah. I have a question. You mentioned that you mentioned earlier that the water on Mars is in ice form, and I believe you mentioned that has something to do with the due to the fact that the atmosphere was stripped away. Can you elaborate a little more on that?
So the ice that we see, or the water that we see on Mars today, is all in that solid form. It's either solid on the polar caps or it's solid in clouds. If we go far enough in the past, we see evidence of liquid water flowing around on the surface. But the real challenge, the $64,000 question, is that Mars really should have been colder in the past than it is today. So why was that water flowing? It's something we still don't completely understand.
So basically, so in a sense, we still are looking for why it's staying in ice form right now.
Well, today, there's not a lot of atmosphere left. So what happens is that any solid on the surface, if you heat it up, it goes directly to a gas phase. It sublimates, just like if you have dry ice, it just turns right to gas. You need to have more surface pressure, more of an atmosphere to keep things liquid. And Mars has lost that, unfortunately, over time.
Thank you.
Yeah, so there's an atmosphere. What's weakening? The gravity field, the magnetic field, the electric field, or B, all of the above?
So there's a couple of ways that you can lose an atmosphere. The two major ways are going to be that, just like any molecule in this room, you've got everything moving around with a certain amount of speed. You go right up to the top of the atmosphere. Some of those molecules have enough speed that they can just fly off into the great unknown of space. We call that Jean's escape, and that's the main way that the Earth's atmosphere disappears. You can also, if you don't have a strong magnetic field to protect the top of your atmosphere, you can also have charged particles and radiation from the sun that comes and strips off those molecules at the top of the atmosphere as well. And on Mars, that's a very important part of the picture.
One thing that's somewhat complex when you judge the Martian is that Mars is contributed for performance. So I was wondering, if you drag all of this Martian soil inside, would you have respiratory issues or some sort of, respiratory poisoning? And you put up a photo of Mars and you said that it would probably be the first thing to happen. But how would you manage that?
It would be a challenge, that's for sure. And one of the problems with a lot of the dust that you find on other planets is that it's very angular. It's not rounded and eroded like on the Earth. The Apollo astronauts got absolutely coated with dust when they went outside of the moon. And when they came back inside, they breathed that stuff and found it quite unpleasant. Dealing with that on a place like Mars would be a big issue. How do you keep the seals on your doors from failing and things like that? And the perchlorate is about 1% of the soil, so you need to find some way to deal with that. As for the movie itself, well, a little bit of dramatic license, perhaps.
You mentioned, well, since you're talking about astrobiology, currently about habitability, but then if it progresses to the point that it would be looking for signs of life itself. But then it comes to the issue of what we can play about cells, yes, viruses, prions, and I guess where is that line?
It is a challenge. I've got to tell you, making a perfect definition of life is really tough. In my classes up in York, when I bring up the concept of astrobiology, we spend a good bit of time talking about, is fire alive? Because many of the things that you define for what makes something alive, you can define for fire as well.
I was just wondering, is there a known species on Earth that might be better suited for proliferating life in the abstract on other planets other than humans, or is going from 0 to humans the best shot?
Well, the big advantage that we humans have is we can build a spaceship. So we can actually carry a little bubble of the environment that's perfect for us to other places. But that said, there are more microorganisms that evolve to fit their environment. And so if we were wanting to go somewhere else, or we were wanting to see a place, we could potentially try to modify what we have. Just to give you one example, we've got, they're called extremophiles, these organisms that can live in unbelievable conditions. One of my favorites is one by the name of Deinococcus radiodurans. This particular type of bacteria was identified in the wastewater from nuclear plants. It's actually inside the core. The reason that we found it is because the radiation kills everything else, but not radiodurans. It can repair its own DNA so fast that it lives in this high radiation environment, and it just doesn't mind.
Whenever I sort of hear about comets, you always hear about it being rocky and icy, and so that's how one guesses everything aggregated and created solar systems, created planets. So are all planets originally the same sort of mix of ice and rock, all of our planets and most of the solar system?
Well, there are trends that we see, and there are places in the solar system where different compounds are stable at different times. So there is actually a trend if you look from Mercury, Venus, Earth, and Mars. All the terrestrial planets are close to the sun. Further out, you've got the gas giants and the icy moons. Essentially what's happening there is you've got a change. As you get further and further away from the sun, you've got places where water ice is stable, floating in space. And the way, the sort of mix that we have in the early solar system is that there's a lot of water out there. So you can actually use it to build planets when you're far out, but not in some. So I don't know if that quite answers your question.
I just wondering, did all planets start as the same sort of mix of rock and ice, and then depending where they are, evolve?
So I guess the short answer to that is no. And it is a bit of a challenge, actually, to figure out where the Earth's water comes from. Because some of the earliest models that were made of the solar system had a very hard time getting any water as close to the sun as the Earth is. Now we've got more computing power, we can have more subtle models of the early solar system. We think we've got that particular problem licked. But it is, you do have differences in different parts of the solar system.
We have time for just one more question right now.
Yeah. Is there any conceivable terraforming technology that could cool down Venus such that as you get it to a habitable temperature? And if such technology exists, some sort of solar limiting thing or greenhouse canceling thing, what would the atmosphere on Venus be like at that point?
Well, there's not a lot of water left. You've mostly got carbon dioxide, and you've got a lot of it, about 90 times as much as we have on the Earth, which also tells you that if you want to get rid of that material, you're going to have to cool Venus's atmosphere very, very severely to get that actually in a condensed form. As far as the technology to do it, a lot of science fiction, a very nice science fiction about this particular problem. In terms of science fact, there's certainly nothing that we have right now, unless the Earth was to devote its entire national property, the entire global output of the economy to cooling Venus. Even then, we probably would have a hard time doing it.
All right, thank you all for your questions. Before I let you go, I'd like to make a few announcements about the rest of the evening. So the remainder of the reception and telescope viewing will not be in this building. You will be guided to the building next door, just across Huron Street. There will be people in red t-shirts, so keep an eye out for them. We encourage you to go over. There will be free food. And before you go, take a moment to